In this video, we will learn about a few more electrophilic additions to alkenes and talk about some of the details of these types of reactions. So the first context is that when we think about strong acid hydration of alkenes, that's fine and it works well as a reaction, but it does have limitations. The first is that you always make the Markovnikov product, so the alcohol ends up on the more substituted carbon. And secondly, when you have strong acids, you're enabling the carbocation intermediate, which then enables rearrangements to occur. And often we don't want rearrangements to occur because we design our molecule a certain way. We put our alkene in a certain place, and we're trying to use the alkene to direct where to place an alcohol. So what that means is that we need other synthetic methods to be able to make these alcohols without rearrangements. So the first reaction we'll look at is called Oxymercuration-demercuration. So it's a two-step process. It follows a three-membered ring transition state, much like the halonium ion formation. And it gets you to the Markovnikov product, and most importantly, it avoids the formation of carbocation intermediates and thus does not undergo any carbocation rearrangements. An example of such a reaction would look like this, where in step 1, you have to use this mercury acetate reagent that reacts with the alkene here, and then the second step is the demercuration step, using sodium borohydride actually as a hydride source to get rid of the mercury, overall getting you to the alcohol product. Just to be clear on why we need this method, if you run this reaction using strong acid and water as your nucleophile, you will get a rearrangement and make a lot of this tertiary alcohol instead of the intended secondary alcohol product. So let's look at a mechanism for this process. The first step is the formation of the positively charged three-membered ring intermediate. So that looks like so. Our mercury, it's easy to forget, our metals often have lone pairs of electrons in their valence shell, and this is then overall a good electrophile that also has a pair of electrons that can kind of bite back to form that three-membered ring. At the same time, we'll have one of our acetates as a leaving group. That gets us to this intermediate here, which is very analogous to what happens during bromination of an alkene. In the second step, then, we have our water as our nucleophile attacking in to break open the ring, thus getting us to our first product here, which is this mercury-containing organic molecule, so an organomercury. And that would look like so after an acid-base reaction. So this is something you would isolate and you could do further reactions on. The most important reaction that you would do is the second step. So these would be two separate experimental steps. In the second step, I would perform this reduction reaction using sodium borohydride. The mechanism for this reaction is not actually known, but it's thought to proceed through some type of free radical intermediate species. Either way, what we should see is that the mercury is essentially just replaced by a hydrogen overall. If you're looking at this reaction, the regioselectivity is going to follow the trend of having the nucleophile attack the more substituted carbon, because that's where more positive charge will be, and that's where it's electrostatically attracted to. And the stereoselectivity, well, it's actually not stereoselective, it's stereospecific, because you only have one possibility of attack here. You have to come from the face of the molecule opposite of where the three-membered ring is. And so there is stereospecificity in this reaction, getting you to the anti-product in all cases. If you're trying to go after the anti-Markovnikov product, then neither the strong acid hydration nor the Oxymercuration-demercuration reaction will be useful. So what chemists came up with in time was a reaction sequence of hydroboration and oxidation. This follows a new type of mechanism that we'll call a concerted or cyclic mechanism. The word concerted for an organic chemist means that everything happens at once and there's no intermediate. So all these previous reactions, we always form some sort of an intermediate first, but in a concerted mechanism, it takes you from the reactants directly to a product. It's also considered cyclic because the electron flow is in a ring. Overall, this yields us. So here's an example of this reaction. I'm going to take the exact same methylbutene and this time use hydroboration-oxidation. The first step is the hydroboration, second step is the oxidation. This molecule here is called borane, BH3. It's a highly flammable gas. The reagent here is not necessarily specific to borane. It could be any other BH containing type of molecule, but usually we're going to expect a neutral boron with a bond to a hydrogen. Overall, that will get us the anti-Markovnikov product where the alcohol is being formed on the less substituted carbon. So let's look at the mechanism to see how that happens. So in the first step, this is, well, the only step really, because this is a concerted mechanism, we get a cyclic process here in which we are taking the nucleophilic pair of pi electrons and attacking the electrophilic boron. The boron's electrophilic because it doesn't have a full octet. At the same time, what we see is then the pair of electrons between the boron and the hydrogen, so that sigma bond, are nucleophilically attacking back. And that overall gets us now to a new bond between carbon and hydrogen here, and carbon and boron there. If you're having trouble visualizing what's happening, it's helpful to see the intermediate of the reaction. So what you can see here is I've set this up so that I have halfway broken the bonds I'm going to break, so the double bond and the BH bond, and I've halfway made the bonds I'm going to make, so the CH and CB bonds here. And so what you see is this transition state has this cyclic nature to it. So this electron flow is kind of all in a cycle. This is a transition state, and then eventually that gets you to the product here. I have an animation for this reaction. Unfortunately, it's a slightly different set of reactants, but it makes the same point. So if you're looking at the animation now, what you should see is a lot of different atoms. The pink atom is the boron, and that's attached to a white hydrogen. And nearby there is a double bond. So let me play this reaction. And you can kind of see as the two molecules get closer and closer together, there is a very momentary formation of a four-membered ring in a transition state. And then that turns into the product quickly. So when you're looking at this step, what you should see is that actually the electrophile here, the boron, is being added to the less substituted carbon. So that pattern is staying the same. Whenever there's an electrophile reacting with an alkene nucleophile, that electrophile is going to the less substituted carbon. The reason that we can get to the overall what looks like an anti-Markovnikov product is because we first use an electrophile here to get onto the less substituted carbon, and then in the second step, this oxidation step, we're turning the BH2 group, or B whatever group here, into an alcohol. The way that works is like this. So again, a second experimental step. I would make a molecule like this one where I've now gone in and turned the H's into just R groups. The reason being that these BH bonds could technically go back and do the same reaction with a second molecule of alkene here. So it's more convenient just to write this as Br2. This reacts with the deprotonated hydrogen peroxide. And so that's coming from the reaction conditions, which has H2O2 and NaOH in it. The pKa of hydrogen peroxide is 11.6, so this is a pretty reasonable acid-base reaction. Deprotonated hydroxide is a nucleophile. That's actually just going to attack the boron, which is electrophilic. That gets us to this type of an intermediate, where we've now caused there to be negative charge on the boron. Because there's negative charge here, and there's an unstable oxygen-oxygen bond, then we get a rearrangement type of process where the carbon-boron bond is going to hop over to form a carbon-oxygen bond instead, and at the same time that will cause a hydroxide to be the leaving group. So there's some sort of analogy to what happens during bromination and also in oxymercuration, where it kind of looks like you have a three-membered ring transition state and a leaving group leaving. That overall gets you to this state, where now we've put the oxygen essentially between the carbon and the boron. That's kind of one way to view it. Overall then, this is going to set us up to do a nucleophilic attack onto boron with our hydroxide, and then overall a substitution is going to take place where the, really this is an alkoxy group here is leaving. That gets you to this point there, and this is an acid-base reaction away from being the alcohol product. So if you're looking at this reaction, you should note a couple things. The first is that it is regioselective. Again, we do prefer to put the boron on the less substituted carbon. And the second thing is that because the reaction happens mechanistically at the important step here all at once, there's no kind of choice in terms of stereochemistry. You have to put the hydrogen and the boron on the same side of the reacting molecules. And so this reaction is regioselective and stereospecific in a syn manner. So the boron and the hydrogen add syn to each other. Along those same lines, then, because of the way the mechanism works down here, the alcohol will appear syn to the hydrogen that's added. A fourth important type of mechanism when it comes to alkene reactions involves what are called carbenes. So carbenes are interesting electrophiles that are not very common, but they react with alkenes concertedly to form cyclopropanes. So first we should go over what a carbene is. This is a carbene, and we want to be very careful because that is not the same thing as a carbanion. They are both going to have a lone pair on carbon here. The difference is that in the carbanion, we also have a hydrogen attached to that carbon so that this carbon has a filled octet. In a carbene, this carbon does not have a filled octet. So if we're looking at the structure of carbene from kind of the orbital perspective, there's two versions of carbene. The singlet carbene is the one that we'll think about. And so that structure will look like this, where there are 3 electron domains around that carbon atom. So this is trigonal planar. One of the pairs of electrons is the unshared pair that's in an sp2 looking orbital, and then we have an empty p orbital that's left on the carbon. You'll notice I didn't put any charge in this p orbital. Really, I could have said that's positive charge here and negative charge in this orbital. Whatever the case is, overall this carbene is going to be a neutral species. That's why I didn't put any charge. So then what we have in this single carbon atom is something a little bit electrophilic because we have an empty orbital, and something a little bit nucleophilic because we have an unshared pair of electrons on carbon, which is not that stable. And so if you think back to some of the other alkene reactions we've seen, we often get this process of the electrophile being attacked by the pi bond, and then the electrophile having a pair of electrons that then attacks back. And so that's exactly what a carbene is set up to do. So a first example of such a reaction would be what's called the alpha elimination of trihalomethanes to form carbenes. A reaction might look like this one here, where we're using tribromomethane, which has a surprisingly low pKa, just 14. And if we use tert butoxide here as base, we can deprotonate this hydrogen, form a carbene, react with an alkene, overall getting us to this dibromocyclopropanated product. All right, let's look at the mechanism for this process. The first part of this mechanism requires us to form a carbene. So how that works is we have tert butoxide, which is a strong base that will deprotonate that hydrogen, and then this pair of electrons that's between carbon and hydrogen has nowhere to go except to be left on this central carbon atom. There's no pi bond for us to make because there's no other leaving groups attached further out past these bromine atoms. Right? So the only place these 2 electrons can go is just to stay on the carbon. If we only did this set of arrows, we'd have 10 electrons around carbon, which is not good. So then we need to break that carbon-bromine bond. That's the leaving group. And because this process is happening on a single carbon atom, this is called an alpha elimination. So the same carbon has both the accepting of the pair of electrons and the leaving of the leaving group. So that's different from beta elimination. One important point I want to make here is that the selection of base here is significant. So this tert butoxide is what's called a sterically hindered base. And this is important because the T-butyl group here takes up so much room that it makes it so even though we have a negative charge on oxygen, it's a very poor nucleophile, just because physically it can't get into the correct spots to do a nucleophilic attack. So because hydrogens are much smaller and much easier to get to, then the acid-base reaction happens much more easily. So the choice of base here is to avoid any unwanted reaction using this as a nucleophile instead of as a base. Once we get to the carbene, then we are reacting with the alkene. That is going to happen like this, where the alkene is going to attack the empty orbital on the carbene, and that carbene pair of electrons is going to attack back. It doesn't really matter which carbon you attach to, because when you form a cyclopropane, it's all symmetric anyway. And so here is the product of that reaction. So we don't really worry about regioselectivity here, but we do have stereospecificity because, again, this electrophile/nucleophile can only react from one face of this pi bond. So we're always going to get our addition to be syn in the product. There is one more version of this reaction that we can look at. So this is a very popular one called the Simmons-Smith cyclopropanation. This one is going to use zinc metal to form carbene equivalents. So we never get to an actual carbene. We get to something that looks like a carbene and is often referred to as a carbenoid or a metal carbenoid. So an example reaction looks like this here, where here's your zinc, and the most common reagent we'll see is diiodomethane. So the mechanism goes like this. The first thing that happens is the formation of the reactive species. So in this reaction, I indicated this is just zinc metal, but we'll also see various types of dialkyl zincs or combinations of zinc with other metals kind of mixed together to form an alloy. They'll all do the same thing, which is overall to form some sort of zinc carbenoid, where what it looks like is the zinc has inserted itself between the carbon and the iodine here. Like so. So now I get a zinc carbon bond. And so the carbenoid is on this carbon here, where this sort of has that character of a carbene, but it isn't so unstable as an actual free carbene. We won't worry about any arrows for that because there's all sorts of ways to explain what's going on there. So what we'll focus on instead is what's happening in the actual cyclopropanation step. Here, what we can see is that the alkene is our nucleophile that's attacking our electrophilic carbenoid. That carbenoid is actually going to use its carbon-zinc bond as our nucleophilic bond to attack back. So I'll do it this way. And at the same time during this attack, what we get is that the carbon-iodine bond is sort of a leaving group, but really it kind of just hops over to the zinc. So this looks like a very messy set of arrows to get to our products here, which are the cyclopropanated molecule and zinc iodide. It's a little bit easier to see if I draw the transition state and set it up like this. So the transition state here has two three-membered rings kind of partially formed. The carbenoid is right here. And so what we're seeing is that the two bonds from the carbon are breaking. A new zinc iodine bond is forming, and two new carbon-carbon bonds are forming. Let me show you an animation of this process. Again, it's not the exact same molecule, but the mechanistic details are the same. So here we're looking at a molecule where the calculation had to be set up with a red oxygen atom to hold the two reactants together. The purple atom at the top there is the iodide. So now what we're seeing is there's only one iodine because the oxygen atom is replacing the other one. So let me press play here. And as you're looking at this, you should see that kind of double three-membered ring transition state form, and that quickly turns into the cyclopropanated product. So that wraps up our look at electrophiles reacting with alkenes as nucleophiles. We talked about a few different types of mechanistic intermediates. Either we see carbocations, or we see three-membered rings that are cationic, or we don't see intermediates at all, actually. We also thought about how these reactions demonstrate regioselectivity, stereoselectivity, and in some cases, the possibility of rearrangements.